Welcome to Online Lecture 5 on stereo naming. Here are the topics that we're going to be covering in today's lecture. So when we're naming stereoisomers, it's important to prioritize the groups attached to chiral centers and double bonds. That's how we distinguish one stereoisomer from another. And to prioritize these groups, there's 3 steps, and so it's important to make sure that you got it right. So step 1. You rank the groups by atomic number of the connecting atom. It sounds complicated. It just means that if you have a chiral center, you look at the atom attached to the chiral center. So a chloro versus a methyl. Chlorine has a higher atomic number than methyl, so that is a higher priority group. And then you break ties with isotopes using atomic mass. That's a rarity, but it's important to know. So for step 2, if there are ties between atoms, meaning maybe a methyl and an ethyl, both of which have a carbon attached, you break ties by looking at subsequent atoms attached to the first one. And so there are a couple of rules with this. First of all, you count double bonded atoms twice and triple bonded atoms 3 times. So each subsequent atom in a chain, if it's a tetrahedral molecule, will have 3 other things attached to it. And then you order the subsequent atoms by priority and then rank them. So for example, a methyl, CH3, has hydrogen, hydrogen, hydrogen attached to the connecting carbon. An ethyl, CH2, CH3, attached to the connecting carbon is a carbon, a hydrogen, and another hydrogen. We're looking at the connecting carbon. And so in the case of the ethyl, prioritizing the connected atoms, this carbon is higher priority than this hydrogen. And therefore, this ethyl takes priority over this methyl. So for step 3, if there are still ties, then you keep going down a chain until the tie is broken. And if you go down to the end of a chain and you still can't break a tie, that essentially means the groups are identical. There's no way that 2 unidentical groups cannot have a tiebreaker. So this has been a little abstract. Let's look at some examples. So identify the chiral centers and then rank the groups. So let's look at the first one. The chiral center is the place where 4 different groups are attached. And in this case, because there's a hydrogen coming off there, this carbon has 4 different groups. He's a chiral center. And so now ranking the 4 groups, you look at the atom attached to the chiral center. So oxygen has the highest atomic number, followed by nitrogen, and then carbon, and then hydrogen, like so. On the next one, again, the chiral center is here because there is a hydrogen. And now ranking these groups, chlorine is the highest atomic number, followed by oxygen, followed by nitrogen, and then hydrogen. Hydrogen, if there's a hydrogen, will always be last. And then for the last one, chiral center is here. It's a good hint that there's a chiral center when you see dash wedge notation on a carbon. So there's a chiral center. The hydrogen is there. And then ranking the groups, fluorine is the highest atomic number, followed by the oxygen on the methoxy, followed by the carbon on this longer chain, and then the hydrogen is last, like that. So when we're naming stereoisomers, we use what's called Kahn-Inholt-Prelog convention. So for chiral centers, we mentioned that each chiral center has 2 different configurations. And so those configurations are denoted as either right-handed, or R, or left-handed, S. So the S comes from Latin for left, so just make sure that you remember the right notation is S. And so to determine whether a chiral center is right or left, we put the lowest priority on the thumb, and then we use the fingers to sweep out 1, 2, and 3, like this. And so when we add R's and S's to an IUPAC name, we do it in one of two ways. You can either put it in the front of the name, enclose it in parentheses, and then indicate the location of each chiral center, or you can put it within the name, putting it in front of the index of each chiral center. Because remember, if a chiral center has 4 different groups, then you'll have substituents always on a chiral center, so you use the index of that substituent to name it. So let's start with an example. Here we've got a chiral center on this carbon, and if we want to prioritize the groups, fluorine comes first. Then we have 2 different carbon groups, but because carbon 13 is higher atomic mass, he's 2. This carbon is 3. This hydrogen is 4. And so if we have to characterize the chiral center, thumb away from us, fingers sweep clockwise, that guy is right. Now to name it, we go back to our normal finding the longest carbon chain, and then we have to number it with the first substituent on the lowest index. So that would start the numbering here, like so. And so the name of this guy would be 4R, because the chiral center is off of carbon 4. And then the groups are 4 fluoro, 1 methoxy, pentane. There you go. Let's look at some more examples, and these are Fisher projections. So remember, a Fisher projection always has vertical bonds going into the board, horizontal bonds coming out, like that. So now let's look at this molecule. On this chiral center, we have 1 for chlorine, nitrogen is 2, carbon is 3, hydrogen is 4. Because hydrogen is on a horizontal bond, our thumb points toward us and our fingers sweep clockwise, and so therefore it is left hand, S. And so now to name it, we find the longest chain, 1, 2, like that. And so we have 1S, and then 1 chloro, 1 nitro, ethane. And now for this carbon here. Again, chlorine is 1, nitrogen is 2, and now between methyl and ethyl, the first carbon has 3 hydrogens attached. The second carbon has a carbon and 2 hydrogens attached here. So comparing this carbon and that hydrogen, this group wins. So this is 3 and this is 4. And so now, because 4 is on a vertical bond, our thumb has to point away from us. And if our thumb points away from us, 1, 2, 3, sweep clockwise, that happens on our right hand. And so now naming it, the longest carbon chain, 1, 2, 3, 4, in that order. So we have 2R, and then 2 chloro, 2 nitro, butane. There you go. So for this next example, we have 2 chiral centers. First, we have this carbon, which has an oxygen and a hydrogen. So those are the 1 and 4. But then there are 2 other groups, a carbon and a carbon. So we have to rank the connected atoms. So this carbon has 3 H's. this carbon has an O, a C, and an H. So comparing that O to that H, this group wins. So 2, 3. And so the first chiral center, if we point our thumb toward us, the numbers sweep clockwise, so it's S. Like that. For the second chiral center, now we have an O being priority 1, and then we have 3 groups all with carbon. So the top group has an oxygen, a carbon, and a hydrogen connected. The methyl has 3 hydrogens connected. And then the bottom group has a carbon, a hydrogen, and a hydrogen connected. And so this group is 2, this group is 3, the methyl is 4. And so now the thumb points toward us again, because 4 is on a horizontal group. The fingers sweep counterclockwise, and that happens on our right hand. And so now when we name it, we have to make sure to account for both chiral centers. So the longest chain is going to start here. It's 6 carbons long, and so we have 2S, 3R. And so methoxy comes before methyl alphabetically. So we have 2, 3 dimethoxy, because there are 2, 3 methyl, hexane. Like that.